In this video, we're going to have a look at how we can solve the values of theta for functions that have undergone period dilation. So considering this example here, we've got sine of 2 theta equals negative root 3 over 2, and we want to find all of the values for theta here over a domain of negative pi and pi. So comparing to the previous ones we've done, we didn't have any dilation at all. But to solve these particular problems, there's not a whole lot different to it, but rather we're going to add a step at the start and a step at the end to make everything nice and easy for us. So consider we've got sine 2 theta. So the dilation of this function, what it's going to do is it's going to compress everything along the horizontal axis, or the x-axis, or the theta axis. So rather than having a period of 2 pi radians, what we're going to get is simply a period of pi radians, because this factor of 2 in here is going to double or speed everything up in terms of theta by a factor of 2. So the first thing I'm going to do is, I don't want to have to deal with this. I just want to deal with something that hasn't been dilated. So I'm going to say let x equal 2 theta. And what this will do is it will say sine of x equals negative root 3 on 2, and therefore our domain is going to change. We're no longer talking in terms of theta, we're talking in terms of x over 2, and that's a 2, and negative pi and pi. And the reason I write x over 2 is because x equals 2 theta, so a single theta is half of an x. Now this still isn't acceptable. I want to make it such that it's easier to read. So rather than saying x over 2 is this domain, I'll say what's the domain simply in terms of x, and it's going to be 2 pi, so negative 2 pi and 2 pi. So what we've got here is sine of x equals negative root 3 over 2 for this domain here. So this is much cleaner compared to what we had done before. Now the second nuance that we're seeing in this case is, notice that we've got a negative sign here. So in the previous ones we were dealing with positive, but now we've got a negative. And it might look like this will throw a spanner in the works, but it actually doesn't do much at all. So consider our unit circle. Consider our unit circle, and we're going to use the unit circle to define the behavior of sine. So we'll say f of x equals sine of x. And what we're going to say is that we're going to ask ourselves, where is sine positive here? So we've got the mnemonic all stations to central. And what this mnemonic tells us is that in the quadrants 1 and quadrants 2, we're going to expect positive values for sine. And for quadrants 3 and quadrants 4, we're going to expect negative. So that shouldn't be an O, that should be a C, sorry. So we're going to expect negatives for quadrants 3 and 4. Now notice the ratio we're working with here is it's sine of x equals negative root 3 over 2. So we've got this negative sign here. So what this tells us is the output of the sine for this value of theta is we're expecting a theta in quadrants 3 and quadrants 4. So if we go up a little, what we're expecting is we're going to get theta here. It's going to be, we're not going to have an internal or an interior angle as a solution. We're going to get a theta from quadrant 3 and quadrant 4. So theta equals the pi radians plus the interior angle. So the interior angle being the, where are we? So the interior angle being the sine of, notice I'm going to drop the negative here. I'm just going to write root 3 over 2. because we already know whereabouts it's going to be. It's in quadrant 3 and 4. We want to know the interior angle, so that guy in there, or phi, in this case phi. So simply putting this value in here, we're going to get our phi. So going up, because we're in negative quadrant 3 and 4, we're going to use these two equations here. Theta equals pi plus phi, and theta equals 2 pi minus phi. So I'll grab these and I'll go back up. And put that there just for reference sake. Alright, now going on. So what we said was we're going to drop the negative and we're going to say x equals the inverse sine of root 3 over 2. And root 3 over 2, if I put that in my calculator, I know, in fact, I don't even need to put this in my calculator. I know it's an exact value, and the exact value is going to be pi over 3 radians. And this x here, it's not x, it is phi. Phi being my interior angle of the triangle. So therefore, to get my thetas, my first theta is going to be pi plus phi. And my second one, my second theta is going to be 2 pi minus pi on 3. So calculating the first one is going to be 3 pi on 3 plus pi on 3. And that's going to give me a value of 4 pi over 3. And the second one, that's going to be 6 pi over 3 minus pi over 3. And that's going to be 5 pi over 3. So our first two solutions of x, so x is going to be 4 pi over 3 and 5 pi over 3. But notice the range or the domain we're dealing with here. The domain is x being, or x including values of negative 2 pi and 2 pi. And what we've done is we've only graphed it over over 0 to 2 pi here. So we're missing out on that 2 pi radians in front of the 0. So one way to put it is, if I sketch something really rough here, all I've sketched so far, or calculated so far, is this first cycle there. What I haven't done is this cycle here, so that being 0 radians, this being 2 pi, and then over here, this being negative 2 pi. So a little bit messy, but what I need to do is, and the values are down here. So what I need to do is I need to find the values that are over here. So we're going to calculate these the exact same way in which we calculated the values before. So I'll get rid of this so I've got a little bit more space. And the way in which we can calculate this is we simply say, expand this out. So I'll grab these and I'll move them down, because chronologically these are going to be the last two values I get. So the first value I'm going to get is going to actually be, not sure why I did that. First value I'm going to get is going to be 4 pi minus 2 pi. And the second value I'm going to get is going to be this 5 pi. See if we can fit it in. So 5 pi minus, minus the 2 pi there. So why was it minus 2 pi? Well, if we go over to Desmos and notice notice that we've got our first values here, so 4 pi over 3 and 5 pi over 3, and these guys over here, so these are our other values. So I'll expand that outwards. So these are our other values here, so these purple bars being the range, so negative 2 pi and pi. So our first values are here, and our second values are over here. So they're roughly 2 pi apart, because that's the period of this function. So if we evaluate these, what we'll get is, so evaluating those functions, what we find is that our values of x, so our values of x is negative 2 pi on 3, negative pi on 3, 4 pi on 3, and 5 pi on 3. But remember, we're not done. We're not done here, because the question was asking what values of theta, will come from this expression or from this ratio here. So we have to go back from x back in terms of theta. So recall x is equal to 2 theta. So we can say that theta, so let theta equal x on 2. And if we let theta equal x on 2, then what we find is that for this we're going to get, actually no, I shouldn't say that. I should say, let's say 2 theta equals x. That's what I should have said. So what we're going to get is 2 theta over here, and that's going to be equal to negative 2 pi on 3, pi on negative 2 pi, or pi over 3, 4 pi over 3, and 5 pi over 3. So I need to I need to divide all of these solutions by 2 to get the value of theta. So doing that, I'm going to get 2 pi over 6, and then negative pi over 6, and then 4 pi over 6, and then finally 5 pi over 6. Alright, so I could simplify these down a little bit more, but I'll leave them like that, and we'll go have a look in Desmos what we find. Alright, so back over to Desmos. So our original solutions were negative 2 pi on 3, negative pi on 3, 4 pi on 3, and 5 pi over 3. Now let's convert this back. So our original range was, or domain was pi and, negative pi and pi. And we're not in x, we're in 2 theta. So notice that we've compressed our function here, or the waveform of our function, but we're still looking at negative root 3 over 2. So the solutions for x, for this case, it's going to be negative pi on 3. So going back, we've got negative 2 pi on 3. That simplifies down to negative pi over 3. And the second one is negative pi over 6. So let's have a look. Negative pi over 6, negative pi over 3, negative pi over 6. So negative pi over 6. Then the next one should be 2 pi over 3. So notice we've got 4 pi over 6. We can simplify that down to 2 pi over 3, like so. So 2 pi over 3. And the final one being 5 pi over 6. So 5 pi over 6. So these are all our values for theta over a range of negative pi and pi. So recalling what we did, first we saw that we had a dilated or a period dilated function. So we simply rewrite it in terms of something that's not dilated. So in this case, over here, we're working with a form that we're comfortable working with. And then we simply modify the domain such that we're working over a single period that we can work with. Then it's just business as usual. So looking at whereabouts or what quadrants we're working in, and then identifying the formula for finding our exterior angle here. Then tying it all back together, we simply calculate all of our angles by subbing back in the original value or the original angle here, so 2 theta. So not x, but rather 2 theta. So looks a little bit more complicated, but the process is almost exactly the same.